Like the homework and the exams are not a lot.
What?
Hey, I presented her too. So many patients. There's DS stuff.
Oh, yeah. So
Can you figure out the Florida to be like?
they never.
It's like sweet guy.
I mean, I don't see you on the class, like, I mean, yeah, go right after it, but like. First half of the class. I think we have. You learn how to.
Okay, we should get started. Sorry for the late. Today we're gonna move on to the second part of our course. So we spent, a few weeks talking about mass transfer. Now we're gonna move on to the separation part, right? So, the first topic we're gonna talk about is called single stage equilibrium process. So in this lecture, in this relatively lengthy notes, I will cover degree of freedom analysis, binary vapor liquid equilibrium, isotopes in binary systems, multi-component flash calculation, and ternary liquid-liquid system. Okay. So the simplest separation process we can deal with is one with only is a two-phase system. For example, liquid vapor system. This is kind of the most common one we deal with. In this kind of separation unit, you have two phases, liquid and vapor. And if the system is at equilibrium, right? Typically that means the mass transfer is fast in each phase. So which means each phase is well mixed. And also if there's a reaction, then reaction is fast, right? And in this case, this problem can be solved without considering mass transfer and reaction, right? They are so fast, we can just ignore them. And we only apply equilibrium criteria to the system. And also we take a liquid vapor system, two-phase system as an example. For liquid vapor system, the relative volatility is large or close to zero. That means we talked about this previously. For a liquid vapor system, relative volatility is ratio of the key value of two different species, right? Species I and J. Key value is basically the mole fraction of species I in the vapor phase and in the liquid phase, right? And relative volatility just tell us how, in a relative sense, how volatile species I is compared to species J. And we have demonstrated that if relative volatility of species I and J is close to 1, that means it's impossible to separate them. And if the relative volatility is close to 0 or close to infinity, right, or very large, then it's very easy to separate them, right? So in this case, if all the above conditions are satisfied, then we only need a single stage to achieve desired separation. Right? So this is called single stage equilibrium process. This process, we have a liquid mixture made of several components that is in equilibrium with a vapor phase, right? because the relative volatility is either very large or very small. That means, let's say if the relative volatility is very large, that means Ki is much larger than Kj. That means just species J wants to stay in the vapor phase much than it wants to stay in the liquid phase, right? Whereas in a relative sense, species J wants to stay in the liquid phase relative in the vapor phase, right? Then in this case, at equilibrium, you will have a vapor phase that is reached with species I, and a liquid phase that's reached in species J. That's how you can achieve separation with such one single stage equilibrium process. On the contrary, if you have a relative volatility that's very small, right, then you will have a Aij very small, then you will have a vapor phase that's reached in species J, right, where you don't have much species I, because Aij, the relative volatility is very small. That means Ki, the key value of species I, is very small, right? That means the species I doesn't want to stay in the vapor phase, right? Instead, it wants to stay in the liquid phase. So that's kind of why we call it single stage equilibrium process. So in this scenario, we can separate the mixture with kind of the simplest separation process. But if these conditions are not satisfied, typically we need several steps, a multi-step process or cascade process to do the separation. But for this set of natural notes, we will only look at a single stage equilibrium process. Okay, so the first thing we need to kind of understand is degree of freedom, or Gibbs free rule. The reason we want to kind of understand degree of freedom is that, let's say now we have this closed system, a single stage equilibrium process in which you have a liquid phase that is in equilibrium with a vapor phase, right? And then in order to fully describe this system, and we need to have a list of variables whose values are specified, right? But also there are equations, right? There are, physical constraints that kind of like, constrain all the variables. They are interdependent, right? Based on equilibrium condition, based on mass conservation and energy conservation, right? So for all these variables, although they are interdependent, there will only be a subset of all these variables who are completely independent, right? Which means if you specify those variables, then you can fully describe this system, right? Then degrees of freedom analysis is a method just to help us to figure out, how to do that, right? So let me give you an example, right? Let's say if we start from a system that has 3 components, C stands for component, C equals 3, and 2 phases at equilibrium. So we have a liquid vapor system in equilibrium. In each phase, we have 3 components, right? And can be water, ethanol, methanol, or water, ethanol, glycerol. Now, to fully describe this system, we need to specify the composition of each phase, right? Which is a mole fraction of each species in both the liquid and the vapor phase, right? Here we use Y to stand for the mole fraction in the vapor phase. We use X to stand for the mole fraction in the liquid phase, right? In this case, in this case, because we have 3 species in each phase, then we have 3 Yi and 3 Xi, right? But in a general sense, for C components, right, then we need to have C variables to fully describe the composition of the vapor phase and C variables to describe the composition of the liquid phase. Then we also need to specify the temperature and the pressure of the system. That give us a total number of variables, right? If you add them up together, that's 2C plus 2, right? And in this case, C equals 3. If you put that number in, you will have 8, right? We have 8 variables, right? So if we know the value of these 8 variables, we can fully describe the system, right? We know the composition in the liquid phase, we know the composition of the vapor phase, we know the temperature and the pressure the process is operating at, right? Now, like I said, it's kind of hard to specify the value for 8 variables. So that's when we know that in this system, there are energy balance, there are mole balance, there are also equilibrium constraints that just constrain these 8 variables. So and now let's write down these equations, right? So first, we have the mole fractions in both the liquid and vapor phase. They should sum up to 1, right? In both liquid and vapor phase. So we have one equation for the vapor phase. We have one equation for the liquid phase. In addition, because we specify the system to be at equilibrium, we know at equilibrium, the mole fraction of one species I in the vapor and liquid phase, they are constrained by the key value, right? That's a thermodynamic quantity that's only dependent on the temperature and the pressure. Now we have 3 components. So we will have 3 key values, right, for each of these components in the system. That will give us, if you add them together, there will be C plus 2, 5 equations, right? So we have 8 variables and we have 5 equations, right? Then the degrees of freedom is going to be the difference between the number of variables and the number of equations, which is V, that's F is a degrees of freedom equals V, that's the number of variables, minus the E, that's number of equations. That will give us 3. So we have 3 degrees of freedom. That means for this system, although superficially you have 8 variables, right? There are only 3 independent variables, right? If you specify 3 variables, then all the other variables can become dependent, right? They can be computed based on the equations we specify, right? Based on the thermodynamic condition and the mass and energy conservation. Okay, so and this is like a closed system. For this system, typically what we do is you set the temperature and pressure of the system as well as one mole fraction, right? It could be either Xi or it can be Yi, just any of the mole fraction. You can determine all the remaining mole fractions, right? Or you can set 3 mole fractions and determine Tp, right? But in this case, these 3 mole fractions cannot be all X or Yi. Why is that? Can anybody? Does anyone know why? So we can specify 3 mole fractions, but they cannot be all X's or all Y's. They have to be a combination of X and Y's. Why? So any guess?
You have all the X's, then you don't need the sum of X equals 1, because you already have that from all the variables.
Yes. So the reason here is that now you specify 3 variables so that you can describe the system, right? These 3 variables needs to be independent of each other, right? So that means each variable will provide a new piece of information for you to solve this problem. But if you specify 3 X's, right? X1, X2, then the third X, X3 really doesn't add any new information because you can compute X3, right? by 1 minus x1 minus x2, right? You can also set two temperature and two mole fractions and determine pressure and composition, right? Really, there are many options you can do so. So in general, now let's look at a general case, right? So where we have C components instead of 3 components, then now the number of variables will be in each phase, right? In each phase P, you will have 6, you will have C variables to describe the composition of that phase, right? So in each phase, you have C variables to describe that composition. Then you add up all the variables across all the phases. Then you will have C times P number of variables just to describe the composition of your system. Then you have temperature plus pressure. That give you a total number of variables to be Cp plus 2. And for equations, right, for each phase, we'll have a kind of like mole balance, right? So in each phase, the mole fractions of that phase need to sum up to 1. So you have, in each phase, you'll have 1 equation that will give you P equations. Then at equilibrium, right? So the mole fraction between any 2 phases is constrained by K value, right? Then we have C equations for each, so for each species, we have 1 K value. And let's say for C component, we have C equations, right? Then for between any 2 phases, we have a K value or equivalent of K value, right? So then we'll have P minus 1 multiplied by P minus 1, right? For 2-phase system, P minus 1 is 1, right? Then you have 1 K value for each species. But let's say if you have 3 phases, for example, you have 1 vapor and 2 liquids, 2 immiscible liquids, then you will have 1 set of K values for the vapor phase and the 1 liquid, and you will have another set of K values for the vapor and the other liquid. Okay. Then you add them together. That's bracket P minus 1 plus P. Now that we can compute the degrees of freedom, that's the difference between number of variables and number of equations. That will give you C minus P plus 2, right? So this is Gibbs phase rule, right? But this equation only applies to a system that's closed system, and it does not have extensive variables. So we may not be able to find a solution if we set an impossible choice of intensible variables. So just give one example, as I just asked. You cannot specify 3. So first of all, you have to specify 3 independent variables, right? So each of the variable can provide a new information. There's another case, even though you specify 3 independent variables, you may not be able to find a solution. So can anybody make a guess? Questions? So the question is, now we know that we can compute the degree of freedoms, right? For example, in general's case, we have F degrees of freedom. That means we need to specify F variables, right? Then we can compute all the values for all the other variables, right? Then we can fully define this system, right? But now the problem is when you specify the F variables, they cannot be a random combination of variables. You have to be deliberate when picking them. The first criteria is that these F variables have to be independent of each other, right? So each of them will provide a unique piece of information. But that's not enough. There's another like condition, even though you specify F independent variables, you may not be able to find a solution to the system. Now the question is, can you make a guess what is that scenario?
Need a temperature and pressure where you form the solid rather than a liquid and vapor, then you have it's kind of conflicting with your equation of Ki that relies on it being in a liquid vapor phase.
Yes. So basically, if you specify temperature, pressure, and 1 mole fractions, right? And this temperature and pressure have to make sense. In the extreme case, you may specify a temperature and pressure that is not consistent with the situation here. You're gonna have a liquid vapor equilibrium, but you can specify temperature or vapor. You can specify temperature and pressure that produce a pure vapor phase or pure liquid phase, or even a solid phase, right? That's one possibility. Another possibility is that we know K value is dependent on pressure and temperature, right? Based on the Anton equation, and it's a nonlinear dependence. So let's say if you specify x1 and y1, right? Then you get a key value k1. This key value might not exist. Make sense? Because you can compute, given temperature and pressure, you can compute K using Anton's equation. But if you start from K, you might not be able to find a set of temperature